So when we talk about energy conservation, we have some total amount of energy, which is equal to the total kinetic energy of the system. So that would be all the kinetic energies of all the individual particles added together, plus the potential energy of all the particles in the system based on the different forces that exist. Okay. The potential energy is more or less a record of energy that you have by virtue of your position. Okay, so this is energy by virtue of relative position. You can think of potential energy as being energy that could become motion if an object is allowed to change its position. For instance, if you have a ball on a shelf that is at rest, then it has a high potential energy, but it doesn't have any kinetic energy. However, if you nudge this ball so that it falls down, then just before it hits the ground, it'll have a low potential energy and a high kinetic energy. What's happening is there's a trade-off between energy stored in potential energy by virtue of position to energy of motion. Okay, so as this ball changes its position, it's losing that potential energy and converting it into energy of motion. Okay. Every force has a potential energy associated with it, at least every force that is kind of position dependent. So for instance, if I'm talking about the gravitational field, right, so there's a gravitational field on the Earth, right? And I might have some object that can be, at the bottom of this gravitational field, or at some elevation above the ground, right? And the force that is acting on this ball due to gravity is Fg is equal to mg in the negative j hat direction. That force is present in both here and here. Okay. So what the potential energy is going to be for this force is it's going to be the negative of the work done on the ball in order to move it to that location. So the potential energy for the force of gravity in this example is going to be the negative of the work done by the force of gravity as the ball displaces from the base here to this higher elevation. So I'll call that delta R, and in our case, delta R is going to be hj hat. My force is minus mgj hat, and the work done by the force of gravity is the dot product of those two. It should be minus mgh. You can then substitute that up here, and I get positive mgh is the potential energy of a massive object in the presence of a gravitational field, at least a uniform gravitational field. Okay. So basically what the potential energy is doing is just saying, oh, well, if you had to do negative work to move something to a particular location, then that same force would do positive work if you allowed it to go back where it came from. And if that force did positive work, then you'd be gaining kinetic energy. Whereas when you do negative work, you're taking away kinetic energy. And so basically what it's saying is whenever we do negative work, we're kind of storing the energy implicitly in the position of the object, because if it's allowed to return back to its original position, it'll have kinetic energy, because that force would do positive work in the reverse direction. Now, of course, what this assumes is that the direction of the force isn't going to change as it's getting back to where it started. And so all of this logic applies to what we call conservative forces. to put it simply, if you think of a force field in space, so let's say we have x and y, and there's force vectors acting at different locations in space. I don't know, let's just have some hypothetical, okay? Then a force is conservative if the work done on any closed loop is 0, okay? So if the work done in moving an object from point A to point B and then back to point A is always 0, then the force is conservative. So another way of writing this is I would say for any closed loop, the total work is 0, okay, done by that force. And so then that's where we get this idea that you can kind of recover the work, because that would mean that the work going from A to B would be the negative of the work going from B back to A. Okay. Now, there are forces which are not conservative, or at least practically speaking, they're not conservative. We think all the fundamental forces are conservative, but often due to statistical effects, you really can't detect the conservation properties because the energy ends up going to degrees of freedom that you can't measure. And one of these would be in the case of friction. So if you imagine, there's like a table with two positions A and B, and it's a rough table, so we have some object with a coefficient of friction. The object can go from A to B, and then it can go back, but as it's going to the right, the frictional force is going to point to the left. And as it's going back to the left, the frictional force is going to point to the right? And so in this case, no matter which direction you move this block across the surface, the work done will always be negative. So friction is not conservative, because the work done is always negative. What that means is that when you compute the total work for going from A to B and then going back from B to A, you're going to get the work from A to B plus the work from B to A is going to be strictly less than 0. And so it can't equal 0, and that means that the friction is not a conservative force. Okay, and that's because the direction in which it points changes depending on the direction in which you're moving. A conservative force field would not change its direction based on your motion. At least not if it does work. Okay. So, let's look at a few more examples of potential energy. So, let's consider an object in the presence of the Earth's gravitational field. So you've got like the mass of the Earth, and then you have some radius that's the distance from the Earth's center. We know, let me just kind of draw this a little longer, that if we go from some lower radius to a higher radius, that the force is not going to be constant, right? And in fact, the force depends on what my instantaneous radius is. And so my force of gravity is going to be minus Newton's gravitational constant, the mass of the Earth, the mass of the object, divided by my radius squared in the j-hat direction. And my delta r is going to have to be a dr, and this is going to be a dr j-hat, which accumulates from r1 to r2, right, from some lower radius to a higher radius. So if I compute the work done, going from R1 to R2 by the force of gravity, that's going to be the integral of Fg dot dr from R1 to R2, which is minus G m e m over r squared dot j hat times dr j hat from R1 to R2, which is integral from R1 to R2 of G m e m over r squared with a negative sign dr. The G, m, e, and m, all of those are just constants, so I can pull those out of the integral, and then I'm really just integrating 1 over r squared dr, which is negative 1 over r. So what I'll get is I'll get positive G, m, e, m over r from R1 to R2, which is G, m, e, m over R2, minus G, m, e, m over R1. So if I want the potential energy, it's going to be the negative of the work done of moving from R1, which is a reference point, to some arbitrary position R, which will be negative G m e m over R plus G m e over m over R1. This is what we call a reference point, or reference energy. The normal practice when you're dealing with the force of gravity is to set your reference point at infinitely far away from the planet. And so if we do that, if we take the limit as R1 goes to infinity, then this expression would go to 0, and then we get the potential energy due to the gravitational field. It's just negative G m e m over r. Okay. So this is how you compute the potential energy for an object. You have some position at which you want to know the potential energy. You have a reference point, and you compute the negative of the work done in going from your reference point to the position of interest. And usually you want to set it up so that the constant of integration you get from this reference point, it goes to 0. And so there's a convention here that just take the reference point to be infinitely far away. In my first example, I just didn't have any constant of integration that showed up. It's kind of implied that it was 0 when I considered the elevation of the ground to have no potential energy. Potential energy is only unique up to the addition of a constant. Okay, so if I have potential energy 1 is F of R, and potential energy 2 is F of R plus 6 joules. These are the same. The reason those are considered the same is because motion is going to be in the form of kinetic energy, which is going to manifest itself as changes in potential energy. Okay? So as long as I'm using a consistent potential energy function, either the one on the left or the one on the right, or any other one that's a constant shift relative to those, it is only going to be the changes in that function which are relevant, and the constant won't introduce any changes because the derivative of a constant is 0. So only changes in P are physically meaningful. So only changes in potential energy are physically meaningful, and what we're going to see is that those changes correspond to forces. Okay. So if we recall that a potential energy is a function of some position variable x is the negative integral of, well, let me put it this way. It's the negative of the work done going from some reference position to a final position x. And for any force, that can be written as, f of x dx if I'm working in one dimension. Then you start to see something interesting, which is that the potential energy is really the antiderivative of this force, right? I'm putting primes on these variables just because you generally shouldn't have your integration variable be the same symbol as a bound. Integration variables are dummy variables that take on all the values between the lower bound and the upper bound, and so if you use the same notation, it's actually not quite correct. So I'm putting a prime here where it's understood that x prime is between x0 and x. Okay. Okay, so my potential energy with respect to x is actually the negative antiderivative of the force. And so we get a very nice formula here that the force is the negative derivative of the potential energy with respect to x. Okay. When we're dealing with one-dimensional problems, or problems that can at least be construed in one dimension, we have these kind of two formulas here. That the potential energy is a function of your position variable. It's a negative integral from some reference point to the final point of f of x prime dx prime, and the force is the negative derivative of that potential energy. When we're working in 3 dimensions, we'll work with something called the gradient operator. We're not doing that in this class, but you'll see it if you ever take 2049 or multivariable calculus. And so when we're talking about the gradient operator, this is going to become the force field is the negative gradient of the potential energy. And the integral version is always pretty much just going to be like reference point, final position, force dot dr negative. Okay. So you might see this in the future if you go further with mechanics or calculus. So we've got a few forces that I want to kind of work things out for. So the first is that we have, so we have the potential energy. So let's write the force on the left. So we had Fg is equal to mg, negative mg j hat. And the potential energy for that is mgy, right? If y is the elevation above the ground. Then we have Fg equals minus g m over r squared j hat. The potential energy for that is minus g m over r. Then we have Hooke's law, which is the force is minus k delta r, where r is the displacement of the spring from equilibrium. The potential energy for that is 1/2 k delta r squared. Okay. Or we're often going to just use delta x if we're talking about that in one dimension. And are there any other kind of important ones that I want to talk about? No, this is pretty much it for now. So these are various forms of potential energy, and these are going to show up in energy conservation equations. And so what you're going to have is you're going to have situations where, okay, we got the total energy. It's going to be the total kinetic energy plus the total potential energy. And so, for instance, if we have, say, like a one particle system, I might have like 1/2 mv squared plus mgy, right? And then I'm going to basically have equations where we have energy conservation, where the initial energy is equal to the final energy, assuming no external forces are doing work on the system. And I'll have 1/2 mvi squared plus mgyi is equal to 1/2 mvf squared plus mgyf. And we're going to solve those types of equations to try to find the values of unknown variables. One way to think about potential energy is that it's a way of internalizing forces within our system. Okay, so we have a system, and there are internal forces and external forces. Right? And, so for instance, an external force is just anything in the system that's not accounted for in the energy equations, really. So we might have some external force out here, which we don't really know the exact properties of it. But if we do learn its properties and understand it to be a conservative force, then we can internalize it and turn it into a potential energy that we account for, and therefore we wouldn't consider that to be energy gained or lost. We'd consider it to be energy converted from one form within the system to another. Okay. One of the forces that would be very difficult to do with this practically, but is true in principle, is the friction forces, right? So friction is pretty much always, let's say kinetic friction, is pretty much always an external force when we are talking about energy. And it always does negative work on our system if it does any work at all. One of the reasons for this is that the frictional force really fundamentally is a result of the vibrations of many multiples of Avogadro's number worth of atoms in surfaces, right? So if we have a surface, it has tons and tons and tons of atoms, right? So a typical kind of macroscopic piece of material has something like some multiple of 6.02 times 10 to the 23rd atoms in it, right? And in just a few grams of material. Now, if you have some block sliding across this material, it's going to cause vibrations in these atoms, right? And so these atoms are going to be vibrating and wiggling and wobbling. And basically, what the frictional force really boils down to is that you have vibrational energy modes in all these atoms, and then you have your kinetic energy. So this would be like the potential energy of the vibrations for the first atom, the potential energy of the vibrations for the second atom, third atom, and going on pretty much basically forever. It's the potential energy for the 6.02 times 10 to the 23rd atom. And so if you have some macroscopic amount of energy that's getting distributed more or less uniformly to these atoms per the second law of thermodynamics, then what you're going to end up with is this energy is going to end up being practically nothing at all in each of these guys because there's just so many of them to distribute it to. Okay, so you can imagine if you had like $1 million and you distributed it across like 100 million people, every person would only get a penny, right? So you could think like this is your $1 million and this is all these people getting just 1 penny per person. So to internalize the frictional force within our system, we would have to keep track of a huge number of variables that practically is impossible to keep track of. So in principle, it could be done theoretically, and that's why we consider energy to be conserved, even though there are non-conservative forces. The non-conservative forces pretty much always boil down to circumstances where the number of degrees of freedom are gigantic and we just can't possibly keep track of them in any practical way. Okay. And that is it for the potential energy video.